So welcome back to this short last part. So basically, the last thing we covered was rather not the last thing. We talked about the standard normal distribution, and we said it's basically a normal distribution where you have where you have mu is equal to 0. Over here, mu is equal to 0. It is centered around 0, and the standard deviation is 1. So you have such a normal distribution. You can actually get the probability density function, because we said you have let's just get a new equation over here. So you say we have p of x, right? Is going to be not really p. Let me do uppercase p to mean this is really the cumulative probability. Is equal to 1. You need an equation, so 1 over 2 pi. I think that is sigma 2. I actually also have to check this. It's not something that you can easily put in your head. Yeah, sigma 2 pi e, right? So you have the equation, which is so that is sigma. Then you have the root symbol. Where do you get that? So you have a radical 2 pi. That's probably under here. Or can I get pi? Do I have pi here? Okay, maybe let me just write the actual pi, and you want to have all of this so it's basically 2 pi e to the x minus mu squared to sigma squared. So where are we? Yeah, so you have this, then you have the exponential, then you have x minus mu, actually this is also exponentiated. So this is a little fraction over here, and you have, it is to this power. The power is also exponentiated, yeah? So you have the power being exponentiated. Okay. So that's a minus. So there's lots of exponents, so don't worry too much about this formula. I'm just reproducing it here for another reason. I said in general this would actually be provided. X minus mu squared over sigma. Why did I have sigma before? Sigma. Wait, this is an exponent too, yeah? Just a minute. So you have that, and it's squared, and you have, okay, it's getting really difficult to select all the little things. So let's have that. Then you have sigma controls. Can I really get this? Maybe I need a bigger screen. Okay, it's becoming really hard to get. So basically, when mu is equal to when mu is equal to 0 and sigma is equal to 1, I wanted to do this practically. So just bear with me for a bit. Where were we? So that's pi 1 over root 2 pi e to the x minus mu. So if mu is equal to 0, so this actually becomes e x minus mu. So that is simply x to the x squared, yeah. So if mu is equal to 0, then this is actually just x squared for the standard normal distribution. And then if sigma is 1, then that is just 2, right? So this actually simplifies out to be only 2. So this is what I wanted to show. Okay, so where were we? Just a minute. So yeah, so this is just 2, and that is x squared. I have to insert one of these. So that is just x squared. So normally we refer to this x as z. We refer to this x as z, or the z value. So for a standard normal distribution, this is going to be the formula, yeah, for the probability distribution function. So it's, again, even for the standard normal distribution, this is not very it's not very useful to remember this formula because it's provided. So the cumulative probability tables that we were using before, these are actually for the standard normal distribution. So these cumulative probability tables are for the standard normal distribution, the ones that we had over here. So given any normal distribution, you can actually convert any normal distribution. Given any normal distribution, you can convert to the standard normal distribution by computing the z value. I think this is a very familiar this is really the same formula from chapter 3 for computing the z value. So once you compute the z value for the value, so it's actually the z value that you use to search on the cumulative probability distribution table. Let's just have an example here for the Greer Tire Company. So in this situation, you have some engineering group that have been collecting data for some tires that they produce, and they find that the mean mileage for a tire is 36,500 miles, and the standard deviation is 5,000 miles. So they determined that that this mileage has a normal distribution, and they want to know what percentage of the tires can be expected to last more than 40 miles. So basically, that more than 40,000 miles. So you're basically looking in this situation. So in this situation, you're looking for the probability. So you're looking for the probability that this x is going to be greater than or equal to 40,000 miles. So what you want to do is to get the z value. So the z value is going to be x minus mu. It's going to be I like to use the formula so it looks good. So you have x minus mu over sigma and in this situation, this is going to be what is our x? So it's 40,000 minus 36,500. So you have 40,000 minus 36,500, which is the mean, and this gives you and you want to divide that by the sigma, which is 5,000, and this gives you 0.7. Yeah, so you have a z value of 0.7. So this is what you want to look for in the cumulative probability table. Cumulative probability table is going to give you the probability that x is that x is less than or equal to. So probability that x is less than or equal to 0.7. So you just have to go and check we have to check our cumulative probability table. So we have 0.7 is 0.758. yeah, this is where you have the 0.7, so it's 0.758, so it is actually 0.758, but greater than, you're gonna get 1 minus 0.758, and that should give you the probability, that should give you this value. So 1 minus 0.758, just a minute, 0.758 we said, so we get 0.242, so this should give you 0.242. So this should be the probability that it's going to last more than 40,000. So let's see in the text, this is what they actually get. Is this what they actually get? The Greer company problem. Yeah. So let's see. So that is the answer actually. Yeah. So remember, they asked for percentage. So this is going to be converted. So this is what you should really give for. So you have to be careful about what the question is actually asking for. So 24.2% of your tires are expected to last more than 40,000 miles. So that's pretty much what we're going to cover for the standard normal for the normal probability distribution. Another thing maybe which I did mention is that these tails never actually touch they never actually touch zero, so it just keeps on going till infinity. Yeah, it just keeps on going till infinity. So there's always some probability that x could be some random value here. So you never actually have a zero in the normal probability distribution. So there's another distribution that we could cover, but I'm going to give this to you as a reading assignment. It's called the exponential probability distribution, which is actually related to the Poisson and binomial distributions. So again, it's not very important to memorize the formulae, but then it's very important to understand what it does and where is it important, where is it applied. I'm not going to go into details for this. For going forward, we're going to be using the normal probability distribution a lot. So I think that's what you're going to concentrate on. But you have to be aware of this to know exactly where you apply it. So that's it for chapter 6.